Good morning, good afternoon, good evening from wherever you are in the world. I'm your host and presenter, Asafa Nyamba, together with my colleagues and training instructors, Professor Satyana Loboda and Mike Quimbali. We welcome you to the continuing trainings offered by NASA on the utilization of Earth observation remote sensing data to address various societal applications. This two-day session will focus on how we can apply remote sensing data for climate-sensitive infectious disease risk mapping and prediction. Before continuing, I'm going to give a little brief on the Applied Remote Sensing Training Program, or ARSET. ARSET provides accessible, relevant, and cost-free training on remote sensing satellites, sensors, methods, and tools. Trainings include a variety of applications of satellite data and are tailored to audiences with a variety of experience levels. Some areas of application in these trainings are in agriculture, climate resilience, disasters, ecological conservation, health and air quality, water resources, and wildfires. This training fits within the bucket of health and air quality. ARSET provides trainings both online and in person. Our online trainings are delivered in two formats: live and instructor-led, like today's training, or asynchronous and self-paced. Like NASA's free and accessible data, all our trainings are offered at no cost. We try to offer trainings in more than one language. However, whenever we can, we only use no-cost and open source software and data. We offer trainings at a range of levels so that you can find a training series that fits your level of experience and need. Please visit us at our website to learn more. Okay, as we continue with the training on remote sensing for climate-sensitive infectious diseases, I want to provide an overview of the topic area. So why climate-sensitive infectious diseases? As we have seen, climate-sensitive diseases have been increasing in spread and magnitude over the last 35 years. And we can note that from the increasing number of publications on various vector-borne diseases and various infectious diseases since 1990. Most of these diseases are mosquito-borne, including malaria, chikungunya, dengue, West Nile, and West Nile virus. NASA data can help in detecting climate conditions that lead to the emergence and spread of such diseases and be used in design of early warning systems to enable public health agencies from regional, national to global scale to be able to undertake early preventive measures to minimize the impacts on human populations. So here are examples of NASA climate datasets that can be used in understanding environmental signatures associated with outbreaks of various climate-sensitive diseases. In part, we want to understand how different Earth system components interact and vary through time, from sea surface temperature variability to the impacts on atmospheric dynamics through rainfall, to the impacts of that on the land biosphere, influencing land surface temperature variability and vegetation, all in combination to create conditions for various infectious disease outbreaks. These Earth observation measurements of climate and environment, including those of temperature, humidity, rainfall, vegetation, just to name a few, have an influence of various aspects of the infectious disease cycle through vectors, including vector population dynamics, parasite pathogen development, biting rates of different vectors, habitat conditions, and disease transmission, and so on. So in this training, we have a number of objectives to be able to achieve. These include one, to be able to identify environmental variables and conditions that can be observed from space, which are relevant to climate-sensitive infectious diseases. Two, to identify the steps and tools needed to study climate-sensitive infectious disease outbreaks using remote sensing data. Three, to recognize several remote sensing datasets commonly used to study and focus climate-sensitive infectious diseases, along with the key attributes such as resolution, coverage, latency, and uncertainty. Four, to be able to select appropriate remote sensing datasets for studying climate-sensitive infectious diseases based on the disease characteristics, region of interest, and relevant environmental variables. And lastly, to examine the benefits and challenges of using remote sensing data for studying climate-sensitive infectious diseases through a case study of epidemia, a system tracking and forecasting malaria in Ethiopia, and other alternative approaches. As a prerequisite to this course, we recommend that you take our fundamentals of remote sensing training to familiarize yourself with terminology and concepts you might hear in today's training. Some examples that are important in today's training are what is meant by spatial and temporal resolution of a sensor. What are the differences between true color and false color imagery? And how false color imagery is used to enhance surface features like presence of vegetation or burn scars. Also, an understanding of what is the difference between spectral reflection and emission. And also the aspects of sensor spatial resolution. Okay, so this training will be over 2 days, with part one today covering how remote sensing data can be used to study climate-sensitive infectious diseases. And part two, to follow on, will be covering a case study and an example implementation system on the use of remote sensing to study climate-sensitive infectious diseases with a focus on malaria in Ethiopia. So luckily enough for you all, this training involves homework, which will be posted on the training webpage. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignments before the given due date. Before we delve into details of part one on how remote sensing data can be used to study climate-sensitive infectious diseases, I wanted to provide you with what objectives we have in this part one of the training. One, to understand NASA Earth observation assets and the characteristics which can be used to study climate-sensitive infectious diseases. To be able to describe how remote sensing parameters or variables can be used to monitor disease vector habitats. Three, to list elements of a conceptual framework for disease risk assessment using remote sensing data. To determine direct and indirect Earth observation metrics that can be used to assess disease hazards, exposure, vulnerability within this conceptual framework. To be able to identify several common remote sensing missions and derived variables that can be used to map disease risk and assess disease burden. And lastly, to be able to articulate some elements of common challenges of working with remote sensing data in infectious disease case studies, as well as strategies for overcoming these challenges. Now, some instructions on how to ask questions. Please put your questions in the question box and we will address them at the end of the webinar. Feel free to enter your questions as we go. We will try to get to all the questions during the Q&A session after the webinar. However, any remaining questions will be answered in the Q&A document, which will be posted on the training website about a week after training. After providing an overview of the training and what will be taking place during the 2 days, I would like to introduce to you the instructor for the rest of part one, Professor Tatiana Loboda of the Department of Geographical Sciences at the University of Maryland, College Park. In brief, our research interests include wildland fire, biodiversity, climate change, public health, and the interactions with other human and physical factors of the landscape. Professor Tatiana Loboda, welcome, and the floor is now open and yours. Thank you.
Thank you so much, Asaf, and welcome everybody here. I'm Tatiana Loboda. I am a professor and chair at the Department of Geographical Sciences at the University of Maryland, and I'm very excited to be here today and share with you why we use Earth observations to study climate-sensitive infectious disease. So the first thing I wanted to bring your attention to is just how many satellites we have orbiting the Earth. And this is just the NASA fleet of Earth-observing satellites. Other space agencies, European, Japanese, Brazilian, have their own satellites in orbit. And all these systems are dedicated to observing the Earth systems. But I have to admit that not a single one among these is specifically designated for monitoring infectious diseases. So why are we here today looking at this picture? Infectious disease, by definition, is disease. In our case, it's going to be human, but can be animal, caused by pathogenic organisms. Neither individual humans nor pathogens are directly observable from space. Well, I've been assured that there are some military systems that can monitor individual people, but neither I nor other members of the scientific community really use this data. And the Earth observations that are available to us are not really suitable for monitoring individual organisms, even as large as elephants. So there are studies going back to early 2000s when the first very high resolution imagery became available that focused on trying to monitor elephants. And elephants are big. But even then, with very high resolution imagery, it's very difficult to monitor individual animals. And now there are some approaches that can look at to find the elephants using deep learning algorithms in open areas or look at large herds of ungulates. But that's neither people, not definitely pathogens. So the idea when we're talking about infectious disease monitoring is that we are not monitoring the organisms by themselves, but we are monitoring something that we are going to refer to as disease echo-niche, which is the idea that we borrow from the fields of ecology and disease ecology. So disease echo-niche concept is not really a very widely accepted term yet. This is the term that I have introduced, and it's drawing from the fields of ecology and disease ecology, and the Earth observation data presents an exceptional source of information about various components of a disease echo-niche. So the ecological niche, echo-niche, is a combination of environmental settings and conditions that allow a pathogen to survive, reproduce, and spread. Disease echo-niche, by definition, then encompasses environmental conditions, which is weather and land cover, different vegetation components, different human components on the landscape, interaction with other species. For malaria, for example, which is most of my expertise in, it's going to be interaction with vectors if it's entirely human malaria. If it is Plasmodium nulci malaria, zoonotic malaria, the interaction with other species will include macaques and other possible vectors. And then, of course, it is the host. It's the target host availability and distribution. And for us, it's mostly people. So what generally characterizes disease echo niche is that every component of this echo niche has its own variability and space and time, and they vary at different scales in different ways, and it really creates conditions that are so complex and the interactions that are so complex that every time we go after any specific disease, we need to reconceptualize how these components are going to come together. Earth observations, as I mentioned, offer an exceptional amount of information and just data source for this. First and foremost, they provide extensive, meaning from local to global information about various components of disease echo niche. So Earth observation data come from a variety of satellites, and it includes NASA assets, other other space agency assets, as well as private satellite constellations that deliver imagery, pictures of Earth at very different granularities, which we refer to as spatial resolution or pixel size. So here you see the island of Kalimantan in Indonesia, and we can see the entire island all together at the same time. We can see nearly the entire globe at the same time, or at least daily, using different satellite constellations. But if we zoom in into the area where you see that red circle, that area is very small comparatively, we can see different levels of resolution. The one that you see in the upper left corner is the Landsat image from 1985. It goes back that far. And the one at the bottom right, you see an image from Maxar, a private constellation, which is a very high resolution satellite, which is imaging the Earth at 30-meter resolution. Comparing the two images, 30 meters and 30 centimeters, right, is at this zoom out look, they look nearly identical. But again, if we zoom to the extent of this white box, you can tell the difference in detail between the two satellites is drastic. And that's what different levels of spatial resolution give us. We are now at the point where we can look at individual households, essentially, and from the individual households all the way to the global daily observations at all different granularities. So what allows us to get those different resolutions and different coverage is the constellations of different types of satellites. So the two primary groups of Earth observing satellites include polar orbiting satellites that go around the Earth. They're pretty much staying on the same orbit, and the Earth rotates underneath them, which makes an appearance that the satellite is actually moving around the world. There are different satellites, and they have very different capabilities. So the one that you are seeing the animation for now is MODIS instrument on board of the Aqua satellite, and it images the world at 1 kilometer resolution, so it's very large pixel. And what it's doing, because it has such a large pixel, it can have very large swaths. That's the individual bands that you're seeing appearing on your screen. of imagery, and that allows us to see the entire globe, or almost the entire globe, with small gaps near the equator, as you can see here, almost every day. So daily observations from coarse resolution satellites. If you're looking on your right animation right now, that shows you a constellation of moderate resolution satellites, including Landsat 8 and Landsat 9. They're all together, they're orbiting, and two Sentinel-2 satellites coming from the European Space Agency, and together as a constellation, they are imaging the Earth frequently, but as you can see, their swaths are considerably smaller, and therefore the observations, daily observations from the systems cannot be achieved, but they're still providing quite frequent observations from polar orbiting satellites. The other type of satellites that we have in orbit are geostationary satellites. Those satellites, despite the title stationary, are really orbiting the Earth, but they're orbiting at the same speed as the Earth is rotating. So they are able to kind of focus on exactly the same spot on the Earth's surface as the Earth is rotating around its axis. To get the geostationary satellites into that orbit, the orbit has to be much, much further away from the Earth compared to the polar orbiting. So our geostationary satellites, therefore, usually have a much more coarse footprint, where MODIS, for example, our polar orbiting coarse resolution satellite, is 1 kilometer, goes east and west, is now at 2.5 kilometers, and the older data is even coarser than that, 4 kilometers and coarser. But what we get by losing the pixel resolution is we're gaining how frequently the data is collected. And here we have observations nearly continuously, so we can look at the same spot on the surface for a long period of time and collecting a lot of information, frequently about weather and meteorological components continuously over time. The next importance of Earth observations, what they're giving us, is that we gain the ability to observe environment in ways that is not available to our direct senses. If you look at the graphic on the right, our eyes are set up to observe the world in a very, very narrow range of electromagnetic radiation in the visible light. What satellites allow us to do is observe the world and its components in different ranges of electromagnetic radiation. You may be surprised to hear, but if we had a broader scope of vision, vegetation is really not green. Most of the vegetation is really near infrared. We just are unable to see it, and the best our eyes allow us to see is green. But if you look at your graph on the left of the screen, you will notice, and again, I just wanted to draw your attention to the fact that the scale here is it's a log scale, so the responses differ quite a bit. So in the visible light, the vegetation is not very reflective, but as you go into near infrared, the reflectance peaks substantially higher, and it's much, much easier to distinguish between dry soil and wet soil, and turbid water and clear water, and needle-leaf vegetation like spruce and pine, and broadleaf vegetation like oaks and maples, etc. So this ability to look at different parts of the electromagnetic spectrum is very important. And then we have even more enhanced capabilities by bringing in active remote sensing instruments like radar, which is sensing the Earth at very, very long wavelengths and therefore allows us to see under the cloud cover and under the tree canopy. Here you have an example of monitoring wetlands under the forest canopy in the Amazon, or we can monitor three-dimensional structure of vegetation using LiDAR imagery from the JEDI instrument on the International Space Station. Not only can we see the top of the canopy and then the ground signal, but we can see how the canopy, the density of the canopy, is distributed within the forest structure, and it helps us to characterize the habitat for different species, as well as for vectors and other components of disease recognition. And finally, what we can get from Earth observations. Sometimes we get very direct metrics that describe exactly important components. Looking at this image, you can see vegetation greenness and vegetation distribution, which is in many cases going to be equivalent to habitat availability and habitat quality for different components of disease recognition, specifically for vectors in this case. But what we can also get is the indirect metrics, proxy metrics. For example, in this case, looking at this image, we can see land use and infer the occupational exposure of people on the landscape. We can see the farming and cropping practices and agricultural burning. We can see this is a very good example of plantation forestry, which is palm plantation. And we can also look at the population density, location, living conditions. There is a lot of proxies that we can extract from satellite imagery. So just to summarize, we have a very large fleet of Earth-observing satellite that is collecting comprehensive, and it's truly global to local, repeated daily to weekly to sometimes 15-minute observations, and very diverse in terms of the range of electromagnetic radiation, resolutions, focus, set of images that we can then use to derive direct and indirect metrics that we can compile together to create a robust method to monitor disease recognition. So in the next part of our lecture, I would like to share with you my experience of building a conceptual framework for studying climate-sensitive infectious diseases and how we implemented that, focusing on my previous work in Myanmar malaria early warning case study. So I focused on developing the framework based on the International Intergovernmental Panel on Climate Change conceptual framework for risk assessment. Many of you are going to be familiar with the IPCC risk assessment. It's very well known, and it views risk as an area of overlap between the hazard, exposure, and vulnerability. I applied that same framework to look at malaria. And then for malaria, the hazard becomes really the parasites and the vectors. And the parasites are far too small, and there is honestly nothing remote sensing can do to help you observe the parasites. We're entirely relying on our colleagues in public health and medical research community to provide us information on parasitemia and parasite prevalence in population. But we can do a lot looking at the vectors, vector habitats, assuming vector densities, etc. So in terms of Earth observations, the hazard component is really focused on the vectors. To observe the vectors, the important start is to really think about what is your vector situation there. So for Myanmar, the first consideration is that malaria vector density in Myanmar is incredibly diverse. We have a large number of Anopheles species, about a large number, more than 2 dozen of them are found to carry Plasmodium species parasites, and those are going to be your malaria parasites. And more importantly, the biting behavior and ecology are really reported to differ substantially from the typically assumed nighttime biting within enclosed areas, right? So the very first thing to consider is what is your vector diversity and what's the biting behavior? And the second consideration is the biting behavior and what that makes sense to then monitor within the scope of your early warning system. We know that, again, for the mosquitoes of Mekong region, they bite quite prolifically in both dry and rainy season, and they bite across all kinds of land cover settings, and they are biting equally prolifically in the morning, during the daytime, and at dusk and in the evening. So that consideration becomes also very important in terms of understanding your hazard on the landscape. Then the next consideration is what's the probability of vector occurrence across the landscape? And again, in Myanmar, vectors are distributed across the landscape everywhere, and it is very rare that you will find areas where the probability of species occurrence is low. And there is another component that I frequently show here is if you look at this inset, it shows you present versus absent vector occurrence, and you can see the entire area is really entirely mosquito paradise in terms of conditions, in terms of distribution. So the conclusion from that we have is mosquitoes are abundant year-round, which means for our consideration, we need to continuously monitor the habitat, not just during the rainy season, not just during immediately after the rainy season. It's got to be done continuously throughout the year. We know that numerous species adapted for various habitats. We have tree-dominated, grass and shrub-dominated environments, which means we need to come up with a system that will monitor habitat conditions across all vegetated land cover types, not just a particular land cover type singled out. And we also know that biting occurs during daytime and nighttime, although with different rates for different landscapes, which again, we need to consider both occupational exposure during daytime. So what do people do on the landscape which will expose them to daytime biting, and the dwelling exposure during nighttime to account for the nighttime biting routines. which brings us to exposure. For malaria, exposure really has to deal with people. And it is, as we just established, going to be both occupational exposure during the daytime and dwelling exposure during the nighttime. Most of the time, the data on occupational exposure is non-existent, but that's where satellite observations can provide really unique source of information. The several types of occupation in the area where we worked included working in teak plantations. They are very prevalent and we know they're hazard for malaria outbreaks, mining activities, rain-fed crops, and flooded crops and fishing. So all these types of occupational exposure are directly observable from moderate and very high resolution imagery. So we can get some proxymetrics from Earth observation data that will allow us to estimate occupational exposure. We can also use very high resolution and moderate resolution data to estimate dwelling exposure based on the prevalence of man-made materials in the construction of houses, in the construction of villages, in the settings. We can estimate what the dwelling exposure to nighttime biting is going to be for different populations across the landscape. So when we can summarize our considerations for exposure, the first and foremost is the land use maps that are derivable from remote sensing data can serve as a proxy for occupational exposure. They will not tell you how many people work there, but they will tell you that there is a fraction of the population that is engaged in those activities in the proximity of the villages and populated centers that you have there. It's also important to remember that daily chores and activities also would provide insight into people exposure. So if we have forest cover near populated centers, it's highly likely that people are engaging in daily chores, whether it's wood gathering or plant gathering or hunting or other activities that bring them into contact with the forest dwelling species and biting. So understanding where the different land covers are and how they're distributed across the landscape also helps to provide some insight into the occupational exposure. And finally, the combination of natural and man-made materials in populated areas can also serve as a proxy for dwelling exposure. That brings us to the last component, vulnerability. And vulnerability really addresses two main questions. The first one is, why are some people more likely to get sick? And that one is less likely to be answered with the Earth observing data because it has something to do with the immunity and other components. But the second one, why is it harder to get treatment, is very much, at least in part, answerable using remote sensing data. And the issue here in question is the access to care. It's not only the general availability of care centers that is important. What is also important is the transportation infrastructure that is going to allow people to seek medical care at the point of medical care availability. And in this particular case, what this illustrates is when you are living in a remote rural area where all your roads are fairly small dirt roads, then during monsoon season, your ability to reach medical care are going to be extremely limited simply because during the monsoon um, period, all these roads are frequently washed out, waterlogged, and impassable, and it's going to be very difficult to seek care. So when we're thinking about vulnerability, again, there are different proxies that can be extracted from satellite imagery to estimate socioeconomic standing. If you think about the people who live in the dwellings that I showed in the previous slide, you can estimate by the fact that most of those buildings are built from natural materials. There is no paved roads. It's probably some of the most remote and fairly poor economic settings where people are going to have other conditions that are going to likely impact their ability to seek treatment in addition to just accessibility. And again, depending on the setting of your particular area, you could use nighttime lights to estimate just how economically robust your area is. You could use prevalence of natural building materials. The more man-made materials are found, the more usually robust this area is. And you can also estimate proximity to logging, mining activities, which frequently indicate areas that are housing migrant populations, which are again some of the most poor and disadvantaged communities available. But all these components are always subject to local context. You cannot use nighttime lights effectively in areas where electricity is not a thing. You cannot use natural building materials as an indicator in the area where everybody is using natural building materials. And the same way, proximity to logging and mining also depends on the economic strategies of a particular area and can be indicative of different things. So understanding local context is going to be critical. Another thing that you can use remote sensing data for is identify groupings of displaced population. So refugee camps indicate potentially hyper-vulnerable populations where the outbreaks are very likely. And you can use remote sensing very effectively to do that. And finally, access to care requires knowledge of points of care. That cannot be done from satellite data. But the length and mode and conditions for travel, so road networks, paved versus unpaved, can be mapped from satellite imagery, and their conditions can be estimated based on weather observations. So when we're talking about malaria risk mapping and conceptualizing the whole framework, we're looking at using satellite data very effectively to monitor vector component of the hazard, and that will include combination of satellite observations and entomological surveys. We can use as well remote sensing data with auxiliary spatial data and surveys to estimate the exposure and vulnerability components. So in the next section of this lecture, I would like to tell you a little bit more and give you more details on how we use Earth observation data sets to assess malaria risk in Myanmar and what you would need to do to make those observations helpful. So the very first thing that we did when we started developing our early warning system is develop the base map that is relevant to specifically malaria conditions. There are so many maps and so many things available globally that picking the map that serves your purpose can be very challenging. So, the first thing to do is to identify the goal for why you are developing that map. For us, the goal was to identify land covers and land use components in Myanmar, which are going to be very relevant for malaria risk. After we've done our conceptualization, we identified the parameters, essentially, the classes that are going to be relevant for malaria risk assessment. And that determines the classes that you include here in the legend. We know that the perennial water is important. Impervious surface, which is that man-made materials, is going to help us identify areas that are less vulnerable to malaria. Villages, malaria being the rural disease, we really need to know where the rural population is. Croplands, again, the occupational exposure, and in flooded croplands, we will know where the malaria larval pools are. We need to know where managed forest, that's logging plantations, um, tree plantations, also an important part, etc., etc., etc. So identifying those classes in the legend that are going to be of importance to you to identify and monitor for specifically malaria. And for each class, we didn't only look at the legend, but we also considered how detailed of a knowledge do we need for this class? Can you map villages in Myanmar, for example, using 1 kilometer data? And rural settlements are very small. They get completely lost in 1 kilometer data. So we, by default, know that we need better resolution than that to identify the components we're very interested in. So the next consideration that we had is there's so much work that has already been done, so many data sets that are publicly available. So we don't want to reinvent the wheel. We really want to capitalize on what other people have done and reuse existing data sets as much as possible. But the key to being able to reuse existing data sets is to evaluate how good they are for your purpose. So, is the metric that they use appropriate? There are some data sets that say we map human settlements across the globe and we use man-made materials, impervious surface to do that. Just looking at that definition, I immediately know that they're going to miss half of the rural developments in Myanmar because there's not a shred of man-made materials. So the metric may be appropriate or may not be appropriate. The second component is the spatial resolution right. Again, there are lots of maps at 500-meter resolution, at 1 kilometer resolution, at 30-meter resolution. And I know from experience that 1 kilometer resolution maps are going to be too coarse. I'm not going to see my villages in that resolution. And another important component, what time period does this data set cover, or when was it produced? So there is a fantastic map of settlements that was made in 2015. That sounds recent enough, but knowing how dynamic population is in my area, I know that 2015 is too far back and the situation likely changed. So if I want to use the data, I need something more recent or something that's repeatedly maps things every year or every 5 years. And then the key component also, even if all these metrics the metric is appropriate and the spatial resolution is good and the time period, the question remains, does it work well within my area? There is a lot of data sets available. Many of these data sets are global in scope. So the first thing I would recommend anybody does is just look at the data sets and compare to very high resolution observations. Visual assessment should be your first step, and it frequently is sufficient to give you a quick understanding of whether this data set is good enough to continue. Many data sets are global. Some of them are focused on particular area. So here we're comparing three publicly available data sets, all focused on built-up and settlement areas, right? One that focuses on Mekong area, which should be very good locally. And if you just look at the comparison, it does pick up more settlements than others. But as I'm looking across all of them, and we did our visual comparison, they don't have very good correspondence among themselves. And having looked closely, I'm pretty sure that these are going to be not good enough to capture again those rural populations that I care about so much. And so that means none of them are doing really well for Myanmar villages. And that unfortunately means that I have to develop our own. So we develop only those components that are absolutely needed. And developing a metric from remote sense data is difficult. So my recommendation, if you are forced to do that, find an expert to work with. Anybody can make a classification. There are so many tools available to make a classification that a toddler can make a classification. But making a good, meaningful classification is shockingly difficult. And that's why the people who created those data sets that I showed in the previous slides are very intelligent, very experienced, brilliant, and yet it still continues to be very difficult. So find an expert who can collaborate with you to help you get that going. So we chose to develop human presence dataset specifically to identify those villages in Myanmar that the big datasets were missing. And from our standpoint, it wasn't as important to know exactly the extent of the human dwelling, but we needed to know where people were, where buildings were, where structures were. So our focus was not so much on mapping the full extent, but at identifying the areas where people were. And we developed a data set, and it was very difficult, but we were satisfied that we were picking out the majority of dwellings that we needed to identify to support malaria elimination in the area. And as you again look compared to the existing data sets, we picked up so many more areas of where people are that it really improved our ability to provide useful information to public health professionals. So once we got all our components together and we identified everything and we're happy with individual components, because we pulled components from different data sets, putting them together into a single map is also a challenge. So the key to that is decide a priori which classes are going to be more important than others, and then compile the map in the order of importance in terms of, again, in terms of malaria risk modeling. It all has to be driven by malaria risk, not by any other factors. Once we have our base map, we can proceed to the vector habitat monitoring. So again, start with conceptualizing. What metrics would you consider in monitoring vector habitat? Well, we know that populations are very much controlled by temperatures, both maximum and minimum temperature. So we probably need daily max and min temperature. Precipitation intensity is important, but it's very difficult in Myanmar from observations. So that's a consideration for later. We know that moisture availability that is retained on the landscape is very important. And if you look at the publications, you will notice that precipitation is usually the factor that in some papers comes out as very important and positively correlated with malaria, and in others it's conversely negatively correlated with malaria. And it's primarily because precipitation, just the amount of water that fell on even precipitation intensity, is only one component of what happens with the moisture on the landscape. The second component is, can your landscape retain this moisture, or is it all going to run off and none of it is going to stay? So moisture availability that is retained on the landscape ultimately for us was a much more important metric than the total amount of precipitation that fell. And ultimately, habitat availability. Are there forests for forest-dwelling mosquitoes? Are there grasslands for grass-dwelling mosquitoes? So those are the considerations. So to do that, we selected two metrics from Earth observation data. The first one is the vegetation stress, measured by the normalized difference vegetation index, NDVI, a very common metric usually used. What vegetation stress tells you is how well moisture is retained on the landscape. This is a better metric than total precipitation that fell on the surface. And we also like it to have land surface temperature that gives you daytime and nighttime measurements from MODIS satellites and VIR satellites now that we can be using to do this. If you look in the literature and previous experience, you will notice that MODIS satellite instrument on Terra and Aqua satellites has been used extensively in Earth observations of infectious disease. Unfortunately, MODIS has been in orbit since 1999, which means it's coming to the end of its life. And very soon, both Terra and Aqua satellites will be decommissioned, and MODIS observation will no longer be available into the future. So a lot of projects and a lot of effort is right now going into using the data from visible infrared imaging radiometer suite, VIRS, to pick up the same metrics and the same observations that MODIS was usually used to. They're not directly comparable, but it should still work fairly well for land surface temperature and for vegetation stress. So once we know what our metrics are, what do we need to consider in terms of parameters? So how high of a spatial resolution we need? Do we need 30-meter resolution to look at vegetation stress or land surface temperature? And the reality is, no, we really do not. Land surface at 500 meters or 1 kilometer observations is perfectly sufficient. And the vegetation stress without human interference does not vary on 30-meter resolution. It really varies on much coarser resolution. So we don't need high spatial resolution, but we definitely need frequent updates. We either need to see it daily or at least weekly, because in time, both vegetation stress and especially land surface temperature can change substantially. So, what we need really is full coverage for the country and frequent observation period. That pretty much tells us that we don't need 30-meter resolution observations. We need coarser observations at high temporal frequency. As a result, we selected moderate resolution imaging spectroradiometer, MODIS, at 250 meters for vegetation stress and land surface temperature at 1 kilometer, which we later downscaled, and I will talk you through what we did. And we used 8-day composites to reduce a little bit the volume of the data that's coming in. So, vector habitat monitoring, and usually when you hear people talk about using Earth observing data and they show you pretty pictures, the pictures look just like this. Everything is clear, every pixel has a value, and everything looks beautiful, and it seems like a very easy thing to do. In reality, Earth observations require a lot of massaging before they become this pretty and very easy to follow. So the key part here is Earth observation data very frequently comes with missing data. There are a lot of gaps in observations, and those gaps require gap filling approaches to make up for the data that wasn't observed. So there are different reasons for missing observations. The most common by far is the presence of cloud and cloud shadow. Very few instruments can penetrate cloud cover, and the majority of the instruments we're working with are certainly impacted by clouds and cloud shadow. As you can see, this is a great illustration here. When you have a cloud in your image, it completely obstructs the surface and you cannot see anything underneath it. And the shadow that it casts takes out a considerable amount of area as well. So, and in one of the earlier images, I showed you this example, and this was a really fun example from Google Earth where they tried to fill clouds, but they didn't quite eliminate all the edges of the cloud in the images. And this is what you are seeing, what these little white outlines are. These are all clouds that the center of the cloud is now replaced with composited data, but the outsides are still visible in the image. So replacing cloud cover and cloud shadows, you can see are still here in the image, is very actually difficult. And they are the primary cause of missing data. Sometimes atmosphere has large concentrations of aerosols, of water vapor, and it's not transparent. So the signal, the electromagnetic radiation does not penetrate it well, and it can create poor visibility. Sometimes we have instrument malfunctioning. The most well-known example of it from Landsat 7, it's an ETM plus sensor, scan corrector died in early 2003, and for at least 5 to 10 years after that, all our imagery for moderate resolution satellite look like that, with gaps in the images where no data is available and there was nothing that could be done about it. And there are other reasons for instrument malfunctioning. When MODIS Stereo just launched, it did not function properly in the beginning, and there are whole months of data that are missing in the data record right now in like 2001 and 2002. So a lot of effort goes into downscaling and gap filling the observations that come from satellites directly. Here's an example of what we've done with land surface temperature data. We have the daytime data and the nighttime data, and what you see here in black is most of it is missing observations, just to highlight how many observations are missing on a particular observation period. I'm showing those in red. And granted, this is in the very beginning of the monsoon season, and you can see that easily 50% or more of the area is actually under cloud cover and is not observed. This really makes it difficult to create a consistent monitoring system. So what we did is we implemented a fairly simple method. Very many methods exist. We took a very simple method, which serves a dual purpose. We're improving the resolution of the land surface temperature data from 1 kilometer to 250 meter, and we are at the same time filling the gaps in observations. And what we did, we adopted the approach that is used for operational fire weather interpolation. They have the same things. They have point source measurements distributed across the landscape, and they want to create a wall-to-wall gridded product. And we took the grid value for valid observations, converted them to points. When you, using the digital elevation model, we knew at what elevation those grid cells were, and we used very simple adiabatic rate to convert the value of the grid cell to remove the impact of elevation so that we brought everything to the sea level. So we still have a lot of gaps, but now all our temperatures appear as if they were at the sea level. Then we interpolate temperature between different valent observations points using 250-meter grid to create contiguous temperature surface at the sea level. And then again, using DEM, we are adjusting for the elevation and taking our sea level temperature and adjusting it to the appropriate elevation for the 250-meter grid. And as a result, we're able to downscale and gap fill our observations and create the land surface temperature estimates. Again, emphasis is here on estimates. This is not now observed. This is really a modeled data sets, but we're getting a fairly good representation of land surface temperature in degrees, both for daytime and nighttime observations contiguously for every single observation period. With creamness, our assumptions and approach has to be somewhat different. Again, it all depends on the conceptual metric, right? The challenge is the same. When the monsoons set in Myanmar, land surface is no longer observable for months. The major assumption is that vegetation generally remains undisturbed. There is no logging, no harvesting, no burning during the monsoon period. And because it is monsoon period, there is no moisture deficit that can put vegetation at stress. So here we're following this assumption, we're taking a different approach. Instead of extrapolating or interpolating in space between different points, we are interpolating values of each pixel over time. We have observation of day 1 and observation on day 2, and we are assuming that the greenness between the two subsequent observations over the same pixel is going to change linearly, and we can then use that and the 3-year average situation to predict the current value of pixel when it's abstracted by cloud cover. And this is what it looks like. So we're able to create our monthly NDVI using our approach, no gaps of observation, despite the fact that from late May through early September, most of the area is not really observable. You can see how we do it here in these two diagrams. If you look at the lower one, it's a little bit probably easier to follow. So the red crosses show the real observations of data. And then from May to mid-September, there are absolutely no observations. So we're linearly interpolating those values between those observations that are available to us, and we can retrospectively understand it. But to monitor in real time, we're combining observations and the 3-year means of past years to say there is a big gap between the last known observation, real observation that we had, and the 3-year mean. So we're going to apply that same gap to the data and estimate where it would be in this particular year based on how vegetation usually behaves in this area. And so that allows us to not only retrospectively fill in the gaps, but also estimate in real time where we would expect the vegetation greenness to be under these conditions. And those are two very different approaches, again, driven by the understanding of the conceptual environment in Myanmar. Estimating occupational exposure is slightly different. Occupational exposure is very tightly linked to land use parameters. For our legend, there are several important keys. Croplands, what people do in crops, and managed forest is what people do in the forest. And the proximity of those land use types and how extensive they are to villages is going to determine what people are engaged with and what's the probability of their occupational exposure. To create robust quantitative assessments, you need a huge amount of basic science. Most areas don't have that. If data is unavailable, we are creating a numeric qualitative reference using land use categories and expert assessments. We're talking to the experts and public health professionals and meteorologists and asking them to help us assign values from 1 to 5, from very low to very high occupational exposure risk in consultation. And that helps us create this kind of exposure category definitions when they know that urban areas people are not susceptible, coastal fisheries very low susceptible, cropping, especially rain-fed crops, moderately forest chores, so proximity to forests is high, and plantation logging and mining is very high, and we're able to create this map combining our base map with the qualitative categories to create the exposure, occupational exposure risk ranging from 1 to 5. Similarly, we used our base map additional data to estimate access to care. So Myanmar is a particularly challenging environment for us because it was almost completely lacking information about rural unpaved transportation routes. As you heard me say many times now, it is the rural disease. So those are of much more important than lovely paved roads that everybody knows where they are. So what we did is we hand digitized roads in rural and most malarious areas of Myanmar using Google Earth imagery. It is possible, it is doable, but it is a tremendous amount of work, and I would definitely not recommend to do that unless it is absolutely necessary. And let me show you what it actually looks like. So we have a GIS layer of medical facilities, and then we used our digitized roads and we computed travel cost time using existing algorithms that are very well known, GIS algorithms for estimating travel cost time. And then we converted that again to the accessibility. So what you can see here in blue is existing roads that are available, which looks like a lot of road cover, right? But when you go to these remote rural areas where the majority of malaria is happening, the actual paved roads constitute a very small fraction of the road network. And the majority of network is was digitized by us. Took us hundreds of hours to do that, but it was key to estimate access to care and create the surface again that goes from low cost to very high cost of access to care and correspondingly low risk to high risk in this sense. And that's what gave us the ability to put together, after a lot more work that I just don't have time or capacity to show here, to put together a wall-to-wall model of malaria burden potential, which ran operationally, or were preparing to run operationally at 250-meter resolution, at a-day update frequency, which provides you 1 to 2 month headway in identifying areas where the malaria risk is escalating. So we executed that between 2016 and 2020. And just as we were about to run it operationally between COVID and the military coup in Myanmar, we lost our connection to the stakeholders and were never able to pass it to the healthcare professionals. But it is a tremendous experience. We learned a lot. And if at any point the public health professionals are ready to take it on, we have it ready for them to use. And so you can see here how over time the conditions are changing, and the conditions are changing at really fine granularity that we are able to capture with this model. If we look at three regions, this is Rakhine State, Sagaing, and Kachin states of Myanmar, some of the very highly impacted regions. You can see over time malaria risk varies. For Kachin and Sagaing, which are both in a very similar ecological niche, they are following very similar trajectory, but they are not identical. Rakhine, which is in a different ecological niche for disease, has a different temporal pattern of risk, both in terms of amplitude and in terms of timing. And that really demonstrates that even though our model is running for the country as a whole, it really is able to pick out local differences. Okay, So just to summarize the components of working with remotely sensed data and what are the common challenges are and how to tackle them in building your frameworks and building your models. The things that I would like to focus on here are the following. So data search and discovery. The amount of data sets that are available is huge. Very many data sets are developed and very many are publicly available. For NASA, the primary repository and the primary center for data discovery is Earth Data Search. All you need to do is establish a login and password identity, and then you have access to all NASA holdings, all the data sets, free of charge, unlimited data access. So this is one of the portals, but it can be overwhelming when everything is in the same place. In addition to NASA specific data sets, there are a lot of other archives and data repositories. So the three that I would like to highlight here is the University of Maryland. So my home department runs a Global Forest Watch data archive and repository where they are providing data on everything related to forest cover change at global scale, 30-meter resolution, everywhere in the world, going very far back and continuing into the future. Another well-known repository is Pangea, and people contribute their data sets there voluntarily. We contributed our Myanmar malaria base map to that repository. And there are also individual NASA data active archive centers that specialized on particular topics. For example, CDAC focuses on social economic data and will be more relevant to identifying human activity. Other data centers and archives focusing on other components. Um, and another thing I would really strongly recommend is simply search the web or use AI. This is a query that I ran using my personal Gemini account, and the query was very, very small, simple, and straightforward. What global data sets are available at 30-meter resolution for urban areas? And it gave me a really, really good summary. It did not pick up all data sets. It gave me some examples, but it also pointed out NASA's socioeconomic data and application center, CDAC, that I mentioned, Earth Data Hub, that I actually don't know much about, but it's very exciting to learn about it, and several others. So it's incredibly easy to find data these days. There are many data points of access. The important things, once you find your data, is to figure out, is this data set appropriate for my applications? And is it good enough? The first thing that I would always encourage you to do is look at the published uncertainties. Every single data set that is published is going to have associated report on data accuracy or uncertainty. The challenges, there are actually two big challenges. Usually these uncertainties are reported for the data set as a whole. So if the data set does really, really well across the globe, it unfortunately does not mean that it does equally well everywhere in the world. There are some areas where it does really well, And there will be some areas where it's going to be doing very poorly. So even if the published uncertainties look really good to you, still look at your area. Another thing about published uncertainties, we like to experiment with them and make them complicated. This is the uncertainties that my own data set is providing in the published document. And it's really hard to understand. I know why we did it. It made sense when we did it. But if you're just grabbing our data set and trying to figure out, is it good enough for your purposes? I would say that our table is probably far too complicated and doesn't make it easy for the users to figure out whether the total uncertainty is appropriate. So conduct an assessment for a specific component. If you need just croplands, look at just croplands. If you need just logging concessions, look just at logging concessions. So look for a specific component in your particular region. And you can do visual assessment. There is nothing wrong starting there. Once you have your data set, if it's existing data set, or whether it is one of the NASA standard data products, you will probably need to do some data pre-processing. And the common things that you would need to do, if it's imagery rather than a data set, or if it's the data product for MODIS, VIRS, and even some other ones, you may need to apply quality assessment bits. Usually MODIS datasets have fantastic idea of providing users with this quality assessment bits. But those are difficult to interpret. Those are difficult to apply. There are tools available that are going to help make it easy. If you just grab the MODIS dataset and look at it, every single pixel will have a value. But without applying quality bits, you don't know whether that value is actually robust or it's almost like my best imagination of what could have been there instead of the really meaningful information. So applying quality bits is a very important part of pre-processing. Once you apply quality bits, you will know where your gaps are. And that means that you might need to gap fill your data. Again, depending on your personal application, you will need to consider what you're going to do about gap filling. There are very many approaches to that. Some of them are very common and simple. Some of them are common and complicated. And some of them are both uncommon and complicated. There's fairly few that are uncommon and simple. But one of the common ones is compositing, taking observations from multiple data sources and putting them together and see if you can composite and get a yearly composite out of the entire year worth of data. A very common way is using maximum NDVI to composite vegetation data. There are other approaches, and again, there is a whole range of those. Another one is interpolating, and those the examples I showed here. You can interpolate in space and you can interpolate in time, right? And both can be valid for a particular data set. And then there are much more complex approaches that involve modeling, either statistical and sometimes physical modeling. Once you gap filled your data, it is likely that your different data sets are going to come at different resolutions. And to make them work together, you have to put them together to a common resolution. If you're going from high resolution, let's say 30 meters, to lower resolution, like 250 meters, it's easy because you have multiple observations that are going into a coarser grid. And that's usually how we do it. It is possible to go from a coarser resolution to a higher resolution by using downscaling. So we aggregate data to coarser grid scales. We downscale data to finer grid cells. And again, multiple approaches are possible. Consider what works best, what makes best sense for your case. And then the final step is you will need to put your data into a common projection so that all your data sets and all your workflows are able to operate on the same scale in the same projection together. So my recommendation when you are selecting a projection is select a projection that will be the best for your final product. When you are showing, when you are displaying, that's probably the best projection that's going to be useful. If you are using your maps to extract area information, how much area is under high risk of malaria, definitely use the equal area projection. If you are just using distance as an important part because you're trying to figure out how close or how to dispatch resources, use an equidistant projection. So, but those are different configurations that you might need to consider. And this concludes my portion of the presentation. Thank you very much for being here. And I'm going to now pass the baton back to Asaf, who is going to summarize the take-home points and tell you more about further resources and what the next steps are. Thank you very much. Asaf, back to you.
Okay, thank you very much, Tatiana, for the excellent presentation and introduction to this topic area. To summarize today's presentation, a few takeaway points that we have to take into consideration. This include: one, satellite observations provide a diverse, comprehensive, and repeated observations of the environment, including both direct and indirect, or proxy measurements, which can improve the assessment and forecasting of climate-sensitive infectious disease outbreaks by monitoring the disease economy that Tatiana talked about. Two, environmental parameters relevant to climate-sensitive infectious diseases and eco-niches such as temperature, precipitation, vegetation, land cover can be observed from space. Three, satellite data might be used to inform hazards, vulnerability, and/or exposure aspects of disease risk. Different considerations apply to each aspect of risk. Four, incorporating remote sensing data into the study of climate-sensitive infectious disease involves identifying remote sensing data with suitable parameters, coverage, resolution, and then evaluating this data for suitability in specific contexts for the application. Existing data sets may be suitable for use, or new locally specific data sets may need to be created. Five, gaps in satellite data may be addressed using gap filling approaches and techniques such as compositing, interpolating, or modeling. And lastly, satellite data processing involves quality filtering, gap filling, regridding, and conversion to a common projection. Okay, looking forward to part 2 of this training. Dr. Mike Quimberly of the University of Oklahoma will present a case study of the application of satellite remote sensing data to malaria forecasting in Ethiopia. Regarding homework and certificates, Homework could be posted on the final day of this training and will be due in 2 weeks. Certificates of completion will be awarded to those who attend 2 live webinars. Attendance is recording automatically. Complete the homework assignment by the deadline. You will receive the certificate via email approximately 2 months after the completion of the course. Here is our contact information. You can also get more information about ARSET trainings via the ARSET website, and you can follow us on the ARSET YouTube channel. Thank you very much for attending today's training. We are now going to transition to the Q&A portion of today's session. Okay, thank you very much. We hope you have enjoyed this part 1 of the training and gained and enhanced your knowledge on the application of Earth observation data on infectious diseases. We are now transitioning to the Q&A session. You had posted some of your questions in the chat room. We have put them all together, and I'm going to ask or read out a number of them, and Professor Tatiana is available to answer them as we go along I'll say for the next 20 minutes. So one of the first questions that was asked in the chat session is, how does satellite imagery help us analyze the specific distribution of vectors? Tatiana?
Thank you, Asaf. So I was trying to keep up with the questions as we went. There are lots of wonderful questions, and I'm going to get to all of them after the session, but we'll start from the beginning. So the specific distribution of vectors is almost impossible to characterize separately from field data collection. So the things that we can do from satellite imagery is to characterize habitat availability. Is there habitat for a specific vector? And what's the quality of that habitat is? But there is no way that we can know what's the vector density or the vector population dynamic is. So ideally, if that is really the target of your work, you would create a robust field survey for vectors that will complement your satellite observations, and then build the models that will link your satellite observations with your field surveys for specific species and distribution of vectors. We, in our work, worked with local entomologists to develop a field survey that was built to mimic what we could observe from the satellite data. And then we used field traps located randomly in different land cover types that were identified in our field data, in our base map, to collect density, presence, and density of mosquitoes using light traps. We did a couple of field seasons and collected some very interesting information. Unfortunately, as I mentioned earlier, we had to stop our work because of dual kind of impact of the pandemic and the military coup in Myanmar. So that was unfortunate. But to summarize, specific distribution of vectors, you will need to pair satellite observations with field surveys, for sure.
Okay, thank you for that answer, Tatiana. So a follow-up question regarding your case study in Myanmar. What kind of species distribution model did you employ?
So again, we were not interested in species distribution. All we needed to know is to conceptualize what kind of land covers presented more danger in terms of malaria transmission. And we looked through the literature and got a really good answer showing that the species, the Anopheles species that carry malaria parasites, are highly diverse, found across different range of land covers. And that's what helped us determine that we needed to monitor across all land covers present in the area. The study that I cite in my slides was actually carried out in, I think, Vietnam, maybe Cambodia, but it's very close to Myanmar. It's in the Great Mekong Delta, and it would be helpful if we had it earlier, but it was very insightful in any case.
Okay, another interesting question is question number 7. Is it possible to use remote sensing data to distinguish between breeding sites that are more likely to spread dengue compared to those that spread malaria?
Yes. So the interesting thing about dengue and malaria, and that the answer actually is going to vary quite a bit based on where you're observing. Because in most of the world, except the newly emerging issue in Africa, malaria, or traditionally malaria has been the rural disease, dengue is the urban disease, and we're talking about two very different species of vector that transmit it. So if you asked me about 10 years ago, I would tell you, yes, the very simple solution is you look for dengue in the cities, you look for malaria in the rural settings. In Africa now, with the emergence of Anopheles stephensi, the vector, the urban vector that can transmit malaria, at that point, it becomes nearly impossible to differentiate at this point where Aedes mosquitoes that transmit dengue and Anopheles stephensi can have their larval breeding sites. And the urban environment is particularly challenging because of the scale of observations. I have talked to several colleagues who are actually engaged in dengue forecasting and trying to understand how to do this. And we're coming to a consensus that we will probably need to engage some drone flights in very dense urban areas to really understand at the very small scale where the water is collecting and where the breeding sites for urban mosquitoes are likely to be.
Okay, thank you for that. Another follow-up interesting question is number 12. Can remote sensing be used for early warning or rapid response to infectious disease outbreaks? And if so, can you provide us with some examples?
So that is essentially the idea behind the early warning system that I introduced. So the thing about why it would work, even though we're using current observations rather than weather forecasts 3 months in advance, there is a definite gap between the change in environmental conditions and the response of the vectors, right? The vector population, the increase, the breeding of female mosquitoes, the larval development, then the transmission of the parasites to humans. So all of that takes time. That's why in our case, we were estimating together with the local experts that the timing between the change in environmental conditions that we were observing and forecasting through our malaria system, early warning system, gave the local healthcare professionals about 1.5, 2 months heads up on where the outbreak is likely to occur so that they can position the resources and personnel and send personnel to areas that they would not normally monitor under these conditions. So this is the entire purpose, essentially, of early warning systems, is to provide support and give some warning to the healthcare professionals and public health professionals in the area.
Now, do you know some examples of these applications?
Well, my application was designed to do this. The one that I showed here, the application that Dr. Wimberly is going to share tomorrow also focuses on that exact point. The point of most of those applications are to provide the advanced warning. And one thing I have to mention is the system that I developed and the one that Dr. Wimberly is going to speak about tomorrow were funded under the Earth to Action program at NASA, which specifically designed to support conversion of research to operations. So within that program, we start our projects in collaboration with the agencies that we're going to transfer the models to run an operational mode. So this is the intent, and this is how these projects are executed.
Thank you very much. Another question. This one is very interesting too. Question number 3. The model you presented, or the approach you presented on exposure, vulnerability, and hazard, can this approach be applied to animal diseases like anthrax? If yes, what kind of data sets might be needed?
This is a great question indeed. So the broad framework really applies to any kind of risk modeling that you can come up with. Unfortunately, I'm not very familiar with the ecology of anthrax, so it's hard for me to conceptualize what needs to be there and how it will distribute between the hazards, the exposure and vulnerability, but presumably your host becomes the animal species that you're interested in, and then you are looking at other components in relation to that host species. Again, the framework is extremely flexible, and I would very, very strongly encourage people to use it. Otherwise, what I have seen in the literature is that people exclusively focus on one component and completely omit both exposure and vulnerability, and therefore present a very lopsided and inaccurate, incomplete representation of risk. And that is a limitation of very many conceptual frameworks and modeling approaches. They focus too much on the vector, but vector is just one component. In some regions, it is such a dominant component that you can get really good relationships between vector population and disease prevalence. But in other areas, that relationship will never stand. And there are other components that are much more important, such as treatments and sometimes bed net distributions and sometimes vector control measures, which are not presented here because we didn't have any of the information or that data present, which is challenging.
Okay, thank you for that answer, Tatiana. Another interesting question is question number 8. In your experience, what types of remote sensing data, for example, vegetation, rainfall, temperature, surface water, are most useful for disease surveillance? I would classify this as a more general question.
I would again go back to that conceptual model and start with what disease are we talking about? Because if we're talking about cholera, right, it's an infectious disease, but it's a waterborne disease. So the importance goes much more towards rainfall, especially extreme rainfall, their ability, the characterization of the environment. Are there poor environments that you could associate with poor sanitation? Are there particular blooms in the nearby water bodies? All that becomes much more important. If we're talking about vector-borne disease, but our vector is ticks rather than mosquitoes, then winter temperatures become a much more important consideration than anything else, because the winter temperatures, not exclusively, by very strongly controlled tick populations in the next year. If we're talking about mosquitoes, then again, we're going back to temperature, surface water availability, moisture, landscape moisture holding capacity. Those are becoming the more dominant issues. So it really depends on start conceptualizing and prioritizing your data sets and parameters based on the disease you're trying to address. That will determine everything.
Okay, another interesting question is number 13. How do you deal with different Earth observations at different spatial resolutions for disease risk assessment?
Yeah, so I alluded to it a little bit in my presentation later. This is probably came in before that came up. So everything ultimately has to be brought to the same functional reporting unit. So if your reporting unit, for us, it was 250 meters, because we wanted to make sure that it was relevant to very specific individual villages and not just aggregated townships. We wanted to keep as much spatial granularity as possible, but being able to run the model effectively. So our first version of the model, which we could run effectively, was at 30-meter resolution, but it was computationally so intensive, and it provided no better answer than essentially 250-meter model, that we settled on 250 as being a much more reasonable reporting unit. And then everything was either aggregated up to that unit or aggregated downscaled from coarser resolution. And there are very many ways of doing it. And I'll give you an example. If you're going from 30 meters and you want to aggregate to the 250 meters, there are many ways. You can go by average, right? If you're looking at 30-meter vegetation greenness, go to 250, you do an average, and that's a reasonable representation. But if you have a land cover map at 30-meter resolution that has discrete classes, you cannot average urban and crops, for example. There is no average between urban and crops. What you can do is you can represent the fraction of urban class within 250 meter pixel, right? The fraction of croplands within 250 meter pixels. Or you can choose what is the dominant land cover type within my 250 meter grid cell from 30-meter resolution. And let's see, 50% of it is cropland, so I'm going to call it cropland. But there are many other considerations. For us, it was very important to capture the rural dwellings. And rural dwellings are small, and if we were to aggregate everything on the dominant site to 250-meter resolution, we would have lost a lot of them. So for us, we went with, for example, are there rural dwellings in this 250-meter pixel? And therefore, we were going to call it rural. It's all going to depend on your priorities and your conceptualization. Again, there's so many people that just throw data into the deep learning model, machine learning, without giving conceptual understanding of what they're trying to achieve, and they get a result, but it becomes entirely not meaningful. So think about really what it is, how the disease function, conceptualize it, and all the decisions are going to be driven by that after the fact. How you upscale, downscale, what the optimal resolution is for you, what data sets make more sense, what you need to prioritize. Start in conversation with medical experts and disease experts, and then involve your colleagues from geospatial data sciences to help you populate the answers.
Okay, now we'll wrap up today's session with question number 32. I have found the dark website sometimes really hard to navigate. Is there an API in Python or R package that we can use that may be developed by NASA?
There are some. I'm not the best person to answer that question. If we have Brock or Carl on the call, maybe they can chime in.
Yeah, hello, this is Carl Mallings. I'm another person in the ARSET program. Hopefully you can hear me. So I guess this is a very general question, but broadly speaking, the NASA Earth Data page, that's the earthdata.nasa.gov link there, is the central landing page for all the NASA data sets. And if you go to that page and navigate through it to specific data sets, there are often links to example codes or examples showing how to access the data sets. I put one example, illustrative example there. This is associated with the harmonized Landsat Sentinel dataset, the HLS dataset. This is a combination of the Landsat data, which was mentioned in the training, as well as the Sentinel mission, which is a similar mission from the European Space Agency. And the data set itself basically combines these two data sets together and harmonizes them. And if you go to that page that's linked there, there's an option for data access and tools. So if you click on that and you scroll down, there's a couple of links with examples to codes developed by the DAC that stores the data, showing how to access the data. Let me just refer to it myself. There's some links to so there's one link there that's a collection of R and Python scripts. There's another link to, it's called Appears, the application for extracting and exploring analysis ready samples. This is an online tool for subsetting and downloading data. So I would say, while there's no sort of single general API or R package that works with every data set, if you're interested in a specific data set, you can look up that data set, either just with an internet search or through the Earth Data page, navigate to the landing page for that data set, and see if there are links to resources that have been developed by the different DACs or by others at NASA, which have examples on how to access the data. And I'll finally say, this is one ARSET training where we're introducing some of these concepts. If you go back through the record of past ARSET trainings, we've given specific trainings which go into more detail on how to, for example, use Landsat data to look at land cover classifications. And there are many times examples or code samples associated with those trainings. So if you're looking to use a specific data set, you can search through the past ARSET training catalog for other trainings which have used that data set, and you might find examples there.
So thank you very much. And on that note, we'll wrap up today's session. We look forward to seeing you again on Thursday at the same time. Thank you very much.